We hear so much about the absolute magic of artificial intelligence. But today, we're going to bridge the gap between those shiny AI concepts and the grueling yet totally fascinating reality of building real-world machine learning models. Welcome to the Practitioner's Pipeline Explainer. Let's dive right in. It's super easy to fall for a common illusion here. As our source material points out, when a product manager hands you, say, 5 years of customer logs and says, hey, we need a prediction on who's going to churn, you cannot just grab that raw data, plug it into some magical machine learning library, and expect a pristine result. Nope, you have to do the heavy lifting of building a carefully crafted dataset first.
Think of this as the data analyst checklist. We're going to cover prepping the raw data, selecting the right algorithm, dodging the overfitting trap, grading your model, and finally, tuning for perfection.
Let's start with Section 1, prepping the raw data, from messy logs to clean feature vectors. Feature engineering is honestly where human creativity really shines. It's incredibly labor-intensive and, rarely automated. You literally have to look at raw server logs and figure out how to extract something meaningful. It's like turning thousands of individual scattered connection timestamps into a highly predictive feature, like average session duration. Pretty much anything measurable can be a feature, but your job is to hunt down the ones with real predictive power. And when you're prepping those features, you're constantly going to face a choice: rescaling numerical data. Why does this matter? Well, if one feature is measured in the thousands and another in tiny fractions, the massive one will just totally unfairly dominate the learning algorithm's gradient descent updates. So you usually choose between normalization, which squashes values into a strict range like 0 to 1, or standardization, which centers your data around a mean of 0. Basically, it's all about putting your features on a totally even playing field before the algorithm even gets a look at them.
Moving on to Section 2, selecting the right algorithm, choosing your cooking method.
Before you write a single line of code, you absolutely must evaluate your real-world constraints. I know it's tempting to just throw a massive neural network at everything, right? But what if your stakeholder needs to understand exactly how a decision was made? That need for explainability immediately points you towards simpler models like decision trees or KNN. You've also got to consider your hardware memory, whether you're working with purely numerical or a mix of categorical data, and honestly, just how fast the model needs to spit out predictions in a live production environment.
Look at how beautifully systematic this scikit-learn cheat sheet is. It maps out the flowchart nature of selecting an algorithm, which completely proves this isn't just guesswork. It's a completely logical path based purely on your data size, whether you have labeled data, and what you're actually trying to predict. For instance, if you have under 100,000 samples and you're predicting a category, the flowchart guides you straight to a linear SVC. It completely takes the guesswork right out of the equation.
All right, Section 3, the overfitting trap, managing the heat.
When you look at these three scenarios, it becomes super clear why perfectly memorizing your training data is just a disaster waiting to happen. On the far right, we see overfitting. The model draws this wild, chaotic 15-degree polynomial curve just to perfectly hit every single data point. The problem? It is literally just learning the random noise in your specific dataset. That means it has high variance and will absolutely fail terribly when you show it new, unseen data. What we really want is that smooth, generalized good fit right in the middle.
So how do we prevent that wild overcomplication? Regularization. Techniques like L1 and L2 regularization basically act as a mathematical leash. By adding a penalty to the objective function when the model gets a bit too complex, it literally forces the model to ignore the useless noise and the weird idiosyncrasies of your training set. You might trade off a tiny bit of accuracy on the training data, but you get a massive boost in reliability out in the real world. Totally worth it.
But once that model is actually built using the training set, we're faced with a really crucial question. How do you actually prove to your product manager that it solves the problem? Like, how do we definitively measure success?
That brings us to Section 4, grading your model, the moment of truth.
Splitting your dataset into 3 distinct subsets, training, validation, and test, is absolutely vital. The training set is exactly what it sounds like. It's what the model learns from. The validation set is your holdout sandbox for tweaking settings. And the test set? That gets locked away until the very end. Testing a model on the exact same data it trained on is quite literally like giving a student the answer key right before the exam. The test set guarantees the model can actually handle data it has never, ever seen before. Now, for classification problems, like predicting if a customer stays or goes, or if an email is spam or not, the confusion matrix is your ultimate scorecard. It's a fairly simple grid, but it directly compares what your model guessed against what the reality actually was. It reveals exactly where your model is getting, well, confused.
Let's take this spam filter scenario. On the diagonal, we have our victories, right? 23 true positives, where we successfully caught the spam, and 556 true negatives, where we rightfully let a normal email through. But look at those 12 false positives. That's when a legitimate and maybe urgent email from your boss gets flagged as spam and hidden away from you. In so many business cases, predicting a false positive is a vastly more costly mistake than a false negative, which is really just seeing a little bit of spam slip in your inbox.
Because of those incredibly costly mistakes, evaluating a model isn't just about total overall accuracy. We almost always have to make a trade-off between precision and recall. Precision basically asks, out of everything the model claimed was spam, how much was actually spam? Recall, on the other hand, asks, out of all the true spam out there in the world, how much did the model actually manage to find? If you want to absolutely guarantee no real emails go to the spam folder, you need high precision, even if it means sacrificing some recall and letting a few junk emails through. It completely depends on what the business actually needs.
Another amazingly powerful tool is the ROC curve, which visualizes the area under the curve, or AUC. A perfect model bows all the way up to the top left corner, giving it an AUC of exactly 1. That means it catches all the positives without triggering any false alarms whatsoever. But look at that graph in the top right, a straight diagonal line with an AUC of 0.5. That means your model is literally no better than just flipping a coin. This is a super fast visual way to compare different models and see if they are actually learning anything remotely useful.
Finally, Section 5, Tuning for Perfection, Tasting and Adjusting.
You see, models have these settings called hyperparameters, like the C value in a support vector machine or the maximum depth of a decision tree. The catch? The algorithm cannot learn these on its own. You, the analyst, have to find them. Grid search is a brute force but highly effective way to do this. You define a list of possible values, maybe on a logarithmic scale, and the computer methodically tests every single combination. You might end up training 14 or even 140 different models on your training data just to see which specific configuration scores the highest on your validation set.
But what on earth happens when you have millions of combinations, or maybe very little data to work with? That's exactly where we use advanced techniques. If your dataset is huge, grid search just takes way too long, so you might pivot to random search or Bayesian optimization, which actually uses past results to smartly guess the next best setting. And if your dataset is tiny, like too small to afford a separate validation set, you use cross-validation. This smartly chops your training data into folds, rotating which slice acts as the validation set, ensuring you can tune your model without needing extra holdout data. It basically lets you squeeze out every last drop of performance.
So, your model is finally deployed. But here is a thought I want to leave you with. As user behaviors inevitably shift over time, will yesterday's perfect model understand tomorrow's new data? The reality is, a data practitioner's job is never truly done. Models out there in production must be continuously monitored, fed new data, and retrained. Thanks for joining me on this explainer, and hey, here's to building more resilient models.